All right, folks, today we're going to talk about transforming graphs. So that could look like a reflection, translation, dilation, just like you talked about in Algebra 2 with the purple note card, those 4 steps. Some things will look a little bit different than what we worked with last year, but we're going to talk about those as we come across them. What I am going to have you do is, in class, work in your groups of 3 to 4 on the front side of your piece of paper. Okay, so questions 1 through 5, and then you'll notice at the bottom of the page you have just a review of your parent functions. We're going to practice sketching those almost every day this chapter so that we make sure we really understand what the original parent functions look like, so that when we get to transforming them, we understand the features that should show up on each of them. Okay, so what I want you to do is pause the video here and work on problems on the front page. I will help you a little bit when it comes to number 5, and then when you're all through with those, we're going to go over some notes to add and some things to look out for as you work through problems like this. Okay, so do that now and come back when you're ready. Okay, so this one I was just looking for in words. You may have decided to write out the translation kind of with the notation that you learned in Algebra 2 with a capital T for translation 3-7, and that's just fine. But then in the next question, I showed you how we're going to write it this year. So this is one of the things that is different. When we talk about the rule, so this is what's important. Okay, when I ask you to write the rule, I'm looking for this a little bit fancier format. And this format helps us talk about not only just where the original point of 0, 0 went to. Okay, if it started at 0, 0, then that ordered pair 3, 7 is precisely the new point. However, what the rule does for us is allows us to talk about translating any point on the graph, not just to 0, 0. Okay, so it's going to be important that we talk about it in this like formula version instead. And all the formula does for us is it allows us to plug in any x and any y value into here, okay, and then get the new ordered pair. So hopefully you remembered from last time with this notation, the 4, -3. What we see in the rule, or what we see on the graph, flips in the equation. Okay, so on your note card that you have, it talks about the general form, f of x equals a on the outside, bx minus h, and these parentheses can be replaced with absolute value. They could have a squared on them, depends on what your parent function is, and then plus k. So this says take the opposite of what you see here, because this is a positive h and this is a negative h, and then the plus k on the side stays the same. Okay, so that's helpful to know, is we're going to see that part switch in the equation. So what I'm going to recommend you do as we go through here is anytime I add notes to the side, okay, you'll notice I did it in a different color. It may be beneficial for you to write these extra notes that we have in some sort of colored pen, so you know that was extra information that I wanted you to realize. You don't necessarily have to change what you ever put down working in your groups, because talking through that information is important. If an equation like this, where there's one right answer, looks different, we want to go ahead and change that. But in terms of something like number 1, either of those say the same thing, so you really don't necessarily need to have both, as long as you understand what the connection is. Okay, so let's talk about the connection to this rule up here that I was talking about. I said the image, or the new point that we wanted to get to using any original point, could be found using this rule. So it says 2, 8 is on the parent function. So remember, our parent function for number 2 was y equals x cubed. And so we're saying if you take this x value and cube it, you get 8. So that's definitely on the parent function. Okay? But then it says give the image under the translation. So we can find the image using the equation, but we could also find the image using just the translation rule, and that's going to be more efficient most times. So here, when we add 4 to an x value on a number line, that means we're going to the right 4. And so we literally mean in our rule, take the original 2, 8 and plug it in. 2 plus 4, just plugging these in here. And then the y value is 8 minus 3. Okay? So 2 plus 4 gives us 6, 8 minus 3 is 5. But if you go to your equation, that should also check out here. So let's talk about this. If I put a little 6 here, 6 minus 4 is 2. 2 cubed is 8. 8 minus 3 is 5. It still works. And the rule is usually faster because you don't have to worry about the parent function necessarily. You just have to add or subtract. Okay. 3 and 4, as long as you remembered it switches on the inside and stays the same on the outside, no problems there. I do want to talk about number 4 just a little bit more in detail here. So these are some notes that I want you to add. When we talk about the parent function of an exponential, there is always a number included for the base. So our parent is y equals base raised to the power of x, but this is a number that we fill in. So our parent function, and you can go ahead and write this, our parent function for this one is y equals 4 to the x. It would be exponential growth. But the rule, when I say rule, I want this formal version now, not just the t. I want the txy. Okay, so I want you to expand on that if you just wrote the t3 negative 5. Okay, we're going to start writing this version instead. Okay? And now let's talk about the rule on a graph. Okay, so these are some notes that are going to be important because you may have switched these up when you were writing them. Okay, so let's talk. When we talk about the rule, it directly relates to graph. Like on that last one, plus meant it went to the right. Okay, so we want to add this directly relates to graph. And it's only in the equation where that part switches. Okay? So here, this parent function at 0, 0 went right 1 and down 3. To say right 1, I need a plus 1 in the rule, and I need a minus 1 in the equation. Both of them get a minus 3 for the down 3. Okay? And we want to find the image. You can use the rule and plug it in if you'd like, or you can just count on the graph since we have it. Here's what I mean by that. Negative 2, 2. Negative 2, 2 is here. And I know everything went right 1 and down 3. So then here's my new point at negative 1, visually. Okay. Take a look at these parent functions here. Again, those were just trying to remember all of those different graphs that we're looking at. Let's review equations real quick. Linear is y equals x, quadratic, y equals x squared, inverse, y equals 1 over x, square root is literally the square root of x, exponential, we've got some base we're working with, growth or decay based on that number, and then cubic is x cubed, inverse square, the only difference here is we see a squared on the bottom, and then absolute value around the x for that last one. Okay, so keep bringing those back to your memory. It's just fine if you have to look them up right now, but we want to get those memorized pretty quickly here, so it makes our life a little bit easier, especially as we get to problems like you see on the back side related to this note card information. Okay, so this note card looks a lot like you had in Algebra 2. The only difference comes right here. And you'll notice, or hopefully you recognized, that the order of the steps has changed. And that's intentional, because really it is important to know that when we talk about order of operations, we do have a scale change or multiplication happen before addition subtraction. The only reason it did not matter in Algebra 2 is 1, we didn't see a lot of dilations, honestly, and 2, we weren't dealing with exponentials very often. So let me show you why that matters. When we think about all of our parent functions, almost all of them go through the point 0, 0, with the exception of the ones with some asymptotes. So this one had the point 0, 1, or more fancy 0a if we do have a vertical scale change. But with that, if we talk about a dilation happening after a translation, that's going to change this one. If I translate that first and then dilate it, it's no longer in the same location. Same thing goes with really 0, 0, but we kind of just ignored the fact that that value would change. And it really shows up and it becomes important when we have to write where that ordered pair goes to. Okay, so in the case of this one, a dilation will change that one. Okay, it wouldn't have changed 0, 0, so that's why it didn't matter that we did it in a different order. And this one's gonna show us here a little bit more clearly what's going on. And in fact, what we're going to do for just a second is talk about how the translation works as well, because I really want to emphasize why this plus h switches in the equation and it didn't switch in the rule, and why that does what it does. And we're going to do so by just looking at some graphs before we get to the equations that you see on your paper. Okay, so I'm going to pull up Desmos here, and we'll work through some practice problems to kind of explain why that works the way it does. Okay, we're going to look at the translation first, but then we'll also talk about dilation, because those are the two things that are opposite on the inside when we look at our grouping symbols for our parent function. So this first example, I just picked on an absolute value, and the graph went to the right 4 and up 3. So my equation shows x minus 4 and then plus 3. So what I want to remind you is of when you graphed something like this by hand, way back when you first learned about absolute values, and you started it kind of like you did with a quadratic equation or a parabola, is you know there's symmetry here around the vertex, and what you had to do to find that point is you had to figure out what made that equal to 0, because our original point was the x value of 0 and the y value of 0. And that's really where this graph relationship to the rule is showing up. So here, if you solve, we've got adding the 4 over, a positive 4. And then plugging that in, 4 minus 4 is 0, plus 3 gives you the regular 3. But it's actually very similar to why the y stays the plus 3 instead of switching. When we think about the rule, we've got t of x, y equals x plus h and y plus k. And both of these things have the x and the thing done to it on the same side, the y and the same thing, or the thing done to it on the same side. So if I want to rearrange this equation here where the y is on the same side as the translation, it would look like minus 3 equals, just subtracting that over. And what we're talking about is what would make these two pieces give me the 0, 0 from the original equation, because that's going to be our translated point. So the value that makes this equal to 0 is 3. 3 minus 3 is 0. And the value that makes this equal to 0 is 4 minus 4. And that's where our 4 and our 3 are coming from. They really both switch, because it's talking about solving for 0, 0. But we're not used to seeing equations like this. We see it where y equals, or the y is by itself. Okay, so it's all about that original point of 0, 0. So a lot of times what I'm going to have you do, instead of thinking about switching what's on the inside, just that memorized rule, what we're going to do instead is take whatever is in the grouping symbols and always set it equal to 0, because every parent function that we're working with the exception of hyperbolas and inverse squares, that 0 being the x value is going to show up, even on those exponential functions. Okay, so we're going to just set that equal to 0. That'll let us find that h translation, and then we can go from there. The next thing I want to talk about is a horizontal structure compression, a dilation on the inside. That was another thing that switches on the inside that you probably didn't talk about a whole lot of why in Algebra 2, so we're going to talk about the focus for that piece next. So I picked the parent function y equals x squared for this one, a quadratic, and you can see those points here all of these x values, which I just did 1 through 5, were squared. And then on the second one, I intentionally picked numbers that could show the relationship more easily. I could have picked 1 through 5 and seen different values, but the reason I chose these is so we can see the compression happening. If you look at your note card, this 2 being greater than 1 on the inside means there's a horizontal compression by a factor of 2. Okay? So let's see that in the graph. My parent function, here's my 1, 1, my 2, 4, my 3, 9 is the red one. So this is my y equals x squared. And then my y equals 2x is skinnier. I'm describing it as horizontally compressed rather than vertically stretched, and it's all about this factor right here. If I say this is horizontally compressed by a factor of 2, I can fairly easily see that on this graph using this table that I was looking at. These x values, if you half them, are giving the exact same y values. You're noticing the relationship here, directly left and right, horizontally. This that was at, let me pick a nicer number. Okay, this one that was at 4, horizontally compressed, was at 2. Okay, so left to right, it literally crunched in half. If I describe this instead as vertically stretched, it's not necessarily going to give that direct relationship, because when we're talking about vertical, we're comparing the y values rather than comparing the x values. And to do that, the parent function actually matters. Here's what I mean. So let's talk about the point on the original, and let's just say 2, 4. If I plug that in here, 2 times 2 is 4, and then squared is 16. So then I would have a 16 that goes with 2 on the other one. And there's the point. Here, if I look at the y value comparison, it wasn't vertically stretched by a factor of 2. It was vertically stretched by a factor of 4 instead, because the parent function, that 2, got squared. So to avoid having to worry about the parent function, we describe this as the horizontal change instead of the vertical change. And what you see is what you get, as long as you remember it does inverse, kind of like what we talked about on the last side. And it all goes back to really how we solve it. Now this one's not as obvious because when we're thinking about 0, we're not going to see it. But just like before, if I take this 2x squared and set it equal to 0, the operation, once I square root both sides, that would get me x by itself is dividing by 2, the inverse operation when we're solving. And so dividing by 2 is what makes it compress rather than stretch. It's all about setting that thing equal to 0, and that's why it's inverse on the inside, or it switches every time. Okay, so we're going to practice some problems. These are on the back side here. And we're actually going to start with the hardest one, so I promise it gets easier after number 6. Okay, it's the hardest one because you haven't done a lot with exponential equations. Okay, but that's what we're going to do to start, is always identify the parent function. For this one, it's 2 to the x. Remember, we have to fill in that number. Okay, so here's what it asks us to do. We want to draw a simple sketch of it and label the transformed point 0, 0 or 0, 1. And then the asymptotes on the sketch. So in order to sketch this, I want you to do it using the 4 steps. So you're required to do 2 things for me, the 1, 2, 3, 4, and the sketch with that labeled point. Okay, so we're starting with 1, 2, 3, 4. We'll have to do a little bit of practice to remember that dilation comes before translation this year. So starting with number 1, we're looking for a reflection of the x-axis. Remember that is a negative out front that flips it over. So let's talk about this original to begin with. 2 to the x is exponential growth, so it goes up like that. Decay would go starting high and going low, with that being a number between 0 and 1. But we do have a negative on the outside for this one. So we have a reflection of the x-axis, and you are welcome to abbreviate. But what we want to do is start thinking about what these pieces do to the graph. So we don't have to do it all at one go when we get to the final graph. So here, a reflection of the x-axis over this line would make this piece come down, and this piece go way down, so it'll actually go down from left to right instead. Okay, kind of like that. with my asymptote still running horizontally. Okay, step 2, we're looking for if there's a dilation. So these are numbers that you don't see addition subtraction with. So we have this 3 here, but this 7 is an addition subtraction, so it'll be in the next step. So it's just this 3. On the outside, that's an A value again, and A occurs with vertical. So what you see is what you get. It's vertically stretched by a factor of 3. That negative we've already taken care of. It's gone after we've talked reflection. Okay, so that's going to, on our graph, take it, and if I vertically stretch this, it gets taller or steeper. Okay, then on step 3, we can do our translation with our little shorthand, just like we did last year. Okay, nothing up with X. Translations will always appear wherever your X is when we're talking about left and right, so there's nothing there. And then 7 on the edge, what you see is what you get. And then reflection over the y-axis, there's a negative with X. That would be a negative up here. There's not one. So now we're ready for our full sketch. Okay, what I'm going to recommend you do is start with the asymptote. Okay, normally we've got this horizontal asymptote at 0. When we reflect it, nothing happens. It's still horizontal at 0. When I vertically stretch or multiply by 3, it's still at 0. Then I'm going to translate it up 7. So y equals 7. And in fact, it is always going to be y equals k, because those first two will never affect the horizontal asymptote. So now we're going to talk about that point. Remember, this point was 0, 1, and we're going to walk through these same steps. So reflection of the x-axis, it's not at 0, 1 anymore, it's flipped over. So it's at 0, negative 1. So I'm just going to write these as we go through here. 1, when I reflect this over the x-axis, 0, 1 goes to 0, negative 1. Okay. Then I'm going to vertically stretch it. Remember, a vertical stretch affects y. So we do have a y value here. We had 0, negative 1, and we want to multiply, since it's a stretch, okay, we're always multiplying, by a factor of 3. So that's 0, negative 3. Okay, and then we're going to translate it. So once we have 0, negative 3, and we're going to translate it, nothing for the first part, so it stays 0. And this 7 says go up 7. So if I add 7 to this, I get to be a positive 4. And there was no step 4. So my final point is at 0, 4. And then I just follow the shape that I sketched here. A vertically stretched, remember, is steeper. And that's it. And it's the toughest one because of that point 0, 1. Okay? So these will help you, but you're just following through those steps. If you remember, and this will help save you 2 steps actually. Okay, if you remember that it's 0a, not 0, 1, that'll get you all the way to a is negative 3. It'll get you all the way to 0, negative 3, and then you just have to apply the translation to that. So that'll get you right there if you remember. Okay, but going through the steps one by one is always your safest bet. Okay, let's look at the next one. Okay, for this one, we don't see parentheses for grouping symbols, so we're just going to tuck them around the x. Okay, and then from there, same thing that we did on the last one. We're going to write out our steps, 1, 2, 3, 4, and look for each of these pieces. Okay, we have a reflection of the x-axis again, with our parent function being y equals x cubed. Normally, that goes up from left to right. So a reflection means it's going to go down from left to right. Just keeping in mind what this is doing as we go through here. Okay, that negative's gone now. 2 is we're looking for numbers that don't have a plus or minus with it, which is nothing for us because that 3 is part of the parent function. So there's no dilation here. We do have a translation, 0, negative 4. And again, no more negatives. Okay, that would be on the inside of the grouping symbols. Getting cubed, nothing there. So this one's a little bit easier. Okay, normally we're starting at 0, 0. reflecting, we know we're going to go down, but it doesn't change where 0, 0 has gone. And then we're going to go 0, negative 4. If you want to do with your points for all of them, you sure can. Okay, 0, 0 under reflection of the x-axis stays the same. Nothing happened here on this one. 0, 0. If I add 0, I'm still at 0. And if I subtract 4, I'm at negative 4. And nothing there, so my final point is 0, negative 4. Following the shape and labeling the point. Okay, a big mistake I see is forgetting to label these points. I will always include that in the instructions, so make sure you're watching out for that. Okay. We're going to look at some different parent functions. That's really the only thing that's new about this year compared to last year, other than the order being switched, is we're going to see not just a line or a parabola or absolute value. We're going to see some of the other ones as well. Okay, number 8 is a parabola. Okay, so it's nothing super new. I do want you to pause the video and try number 8 for me. Okay, work in your groups, or if you were gone, work through that one, and then we'll check it when you're done. All right, for this one, 4 on the inside, remember that's a horizontal compress, because if I were trying to solve this equal to 0, I would have to divide by 4 or make it skinnier left to right by a factor of 4. And then it did go down 2, and that's all that happened. Okay, I didn't have you do number 9 just because it's one of the different parent functions. Okay, this one is y equals 1 over x. So let's talk about what that looks like. Okay, remember 1 over x, we can't divide by 0, so there is an asymptote showing up. And there's one actually at x equals 0 and y equals 0. And instead of talking about the point 0, 0, for this graph, we're going to just label where the asymptotes have moved to, because those were the important features for this graph. Okay. If we have a reflection, that changes where our branches go. If we have a stretch or compression, that just shows how far away these branches are from the asymptote. So all that will be important as we go, but the only thing we need to label are those vertical and horizontal asymptotes. So 1, 2, 3, 4 here. Okay, step 1, we're looking for a negative. I want to point out for this one, if there is an A value, it will appear on top. That's because if we think about what we see here, this 1 over, and then this x minus h plus k, because our x is in the denominator, that means the h has to be there with it. This is like a over 1, and so you won't see the 1 on top, you'll see that a value on top if there is one. Okay, so keep in mind, if you have a vertical stretch or compression or a reflection of the x-axis, it will show up on top. Okay, there is not one here then. We don't see numbers that aren't add and subtract, because that's those next ones for our translation. This, if I solve that for 0, okay, we're adding it over, so it's a positive 2, and then what you see is what you get for the second part. And then there's no negative. It would be right in front of that x if there was one. We don't have one here. A lot of times you're not going to see a bunch of reflection of the y-axis, just as a heads up. Okay? So here, the only thing that happened was a translation, which means the only thing that we have to worry about is where those asymptotes have moved to. And if I'm translating to the right 2, that's going to move this over 2. Dash that on there. Label it. And then 6 upwards. Label it. And then follow your branches like normal. And that's it for those. All right. These ones I'm going to talk you through because there's another thing that's happening here that did not happen in Algebra 2. And you probably don't recognize it, but we're seeing both a B value, a horizontal stretch compression, and an H value, a translation left to right, at the same time. And you never saw those when working with these types of problems in Algebra 2. You did see them with graphing by hand, but it's been a while since you've done that, so we're going to talk about how this changes our process. Okay, so still 1, 2, 3, 4. Still thinking about our parent function. So y equals square root of, absolute value of x makes this little v. The important feature being the vertex. Starting with step 1, looking for reflection over the x-axis. Same process, no negative out front, we're good there. 2, nothing's changed. We still look for numbers that aren't added or subtracted, so that's 2. If we think about solving this thing, we would have to divide that 2 off. So this is a horizontal compression. But this solving is really where part 3 is going to come into play being different. Okay, so this I want you to write out. When we're talking about step 3 here, we are saying 2x plus 8 equals 0. Okay, you can put it below, you can put it here, it does not matter. And we are solving this for the x value. So if I subtract that 8 over, I have 2x equals negative 8. And then I divide by 2, then I get an x value of negative 4. If we thought about this the way we did last year, and just opposite of what you see, that would have said a translation of negative 8. But that's not how we solve these problems when we talked about finding the vertex by hand. We always set that 2x plus 8 equal to 0 to find where 0, 0 was, or the vertex on the parent function. Okay, so you have to set it equal to 0 to solve for the h value. Okay, it's necessary. Because we're talking about something that was, yes, translated negative 8, but it was also horizontally compressed by a factor of 2. If we think about translating it and dividing by that factor of 2, then we have a value of negative 4 instead of negative 8. Okay, so really the translation here is negative 4 and then my positive 5. Okay, so you got to watch out for that. I'm going to make a note. Watch for B with H. Okay. And then step 4, we don't have one. And that's the only thing that's different here. When we talk about this, our ordered pair is at negative 4, 5. And horizontally compressed means this thing gets skinnier by a factor of 2. And then always labeling that point. Okay, so with that in mind, I want you to try number 11. Okay, if you need a reminder of what the parent function looks like, you can flip over to the front side. Okay, but pay attention to step 3 as you go through that one. Okay, you should have gotten an Rx. That means instead of going up to the right, we're going down to the right. Step 2, we have another horizontal compression of 3. Okay, step 3, our translation is negative 2/3, negative 1, because when I take 3x plus 2 and set it equal to 0, I have 3x equals negative 2. X is negative 2 over 3. Okay, and then step 4, nothing on the inside. Okay. If I do have a step 4 in this case, it would mean then I go this way to the left instead, okay, which will happen on occasion. So negative 2/3, negative 1. Horizontally compressed, this is going to make it steeper. If I cut that thing in half this way, or in thirds, excuse me. Something like that. And then we label our point. Okay. Last thing we're going to do is go backwards, and these go quite a bit faster. It gives us the description, and our job is to write the equation. So what I'm going to have you do first here is just write down your generic function for me. And then we'll talk about what's going to change as we go through here. So they gave us some things that happen to a parent function. So we're going to change our parentheses to whatever our parent function is. In this case, it's absolute value, so we just change those to bars. And then we add in numbers for the letters A, B, H, and K based on what we see happening. Okay? The only thing we have to watch out for is those translations and scale changes to make sure if they happen at the same time, we're looking out for how that could affect our numbers on the inside. Okay? Otherwise, it's not so bad. So it says we are translating 4 units to the right. Okay, so translating 4 units to the right, I would need a -4 here. Opposite. Stretch vertically by a factor of 2. Remember, vertically is going to be outside, closest to y. Okay, so that's my 2 here. Reflected over the x-axis, that's also outside. And shifted 3 units downward, that's a -3 here. And then we can just bring down our grouping symbols and our y equals. Notice I didn't bring down b because they didn't say anything about horizontal, and they didn't say anything about reflector of the y-axis. So my final equation, -2 times the absolute value of x minus 4, and then -3. Okay. The next one, go ahead, pause the video, read through, and try that one. Okay, nothing too crazy on it. Okay, vertically compressed is the 2/3. Okay, then we said reflected over the y-axis, so there's a negative inside with x. Shifted 3 units to the left, okay, so that's a +3, and squared, and then 2 units upward. Now here's a weird part that I want to talk about. When we think about this graph, -x plus 3 equals 0, if I solve this one, I would have -x equals -3, and then x equals a +3. So this says I was shifted 3 units to the left, but then reflected over the y-axis. If I was shifted 3 units to the left, okay, that's what this is saying. Okay, when I minus this over, I'm shifted to the left. But then I was reflected over the y-axis, which switches it, because remember, reflection over the y-axis will change that value. Okay, so it's happening in that order. We're fine as it's written. Okay, but there were 2 pieces, a B and an H, happening at the same time, and that's something to look out for. Okay, so let's look at this last one. It says horizontally compressed by a factor of 5, reflector over the x-axis, translated 9.9 units upward and 2 units to the left. Okay, so starting out, again, we're just talking about how our grouping symbols changed. In this case, we're going to have a squared show up, and we're filling in stuff. So horizontally compressed by a factor of 5 would have a 5 right here. Go ahead and put my x down. Reflected over the x-axis is going to have a negative out front. Translated 9 units upward. That's a plus 9.9. And then it says 2 units to the left. So if I want to go left, I need a plus 2. Okay? So let's talk about this. This would say 2 units to the left, and then horizontally compressed. Okay, but this one, the order is not actually written that way. It says horizontally compressed by a factor of 5, and then it doesn't say translated until the end. Okay, so these ones are kind of tricky, where when you had to write sentences back in Algebra 2, the order of your sentence mattered. Okay, this is kind of the same idea. The order of the sentence really does kind of affect what it means. So they're a little bit tricky here. And for the purpose of this, here's what I want you to do always. And it's a weird exception when there's a reflection. But I always want you to do it this way if there is a number in front, because this is how they're going to be written normally in this order. Is what I want you to do is when you are talking about writing it for this direction, if you want the translation to say what it's supposed to say, so it's supposed to say 2 units to the left, and right now it's saying that we're having our vertex at -2/5 instead. Okay, if we want it to say what it means, then what we have to do is just make sure when it's solved, it solves to be 2. The easiest way to do that is by adding an extra set of parentheses. And it seems weird, but let me show you how it works. Okay, so if I rewrite this, 5 times quantity x plus 2, and then we square it. Okay, this becomes something we can simplify to a nice 5x plus 10 getting squared. Everything else coming down. And then if I go over here, 5x plus 10 equals 0, I've got a 5x equals negative 10, and that tells me x is that negative 2, the translation to the left like I wanted it to be. Okay, so when you see b with h, what you're going to do with these sentences is always write b factored out. You don't have to worry about that with just a reflection of the y-axis, but you do have to if there's a horizontal stretch or compression. Okay, so horizontal something. Okay, it'll help when we see those as we go through problems. Okay, but that's the toughest thing you'll see. As always, if you have any questions as you go through your homework, okay, be sure you check your answers on the key and then come see me with any problems.